All right, hello everyone. Yeah, welcome to today's installment of Paleo Perks. Sorry for the technical mix-up. Um, but today we'll be hearing from, and actually, Jeet, can you pronounce your name again? I think my internet
Yeah,
cut out
sure.
right when I,
Yeah, that time you had a problem. Yeah,
yeah,
it's Jeet Majumdar.
Jeet Majumder. Okay, well, yeah, thank
Yeah,
you, Jeet, for
exactly.
agreeing to give a seminar today. Um,
Yeah, thanks
and
to you.
Yeah, and so we'll be hearing about reconstructing monsoon-induced oceanographic variations in the Eastern Arabian Sea since Marine Isotope Stage 3, insights from foraminifera and pteropods. So, a bit about some housekeeping. So we'll start off today with the welcome and announcements, um, and then we'll have the talk itself, which should last about 30 minutes. Then we'll move into a moderated question and answer session. And during the question and answer session, you can send your questions to the questions at PaleoPerks host. After that, if Jeet is up for it, we can have a little tea time, which is just a more informal, um, opportunity to get to chit chat and get to know our speaker a little bit more. And that's totally flexible, totally casual. Jeet, does that work for you? I think in the email
Yeah,
you.
yeah. I in the email I said yeah, I have no problem for a tea time talk. I mean,
Great.
this tea time discussion. Yeah, it's fine.
Great. So it's very casual, and I think a lot of our kind of regular Paleo Perks attendees kind of know how it goes. So yeah. Anyways, that will be after the talk. So a bit of Paleo Perks housekeeping. Paleo Perks values the participation of all folks interested in the paleo sciences. Please remember to abide by our code of conduct during today's seminar. Please mute yourself during the duration of today's talk. And if you find yourself unmuted at any point, please mute yourself out of respect for our speaker. Uh, again, you can ask questions by chatting with the questions at Paleo Perks host, or alternatively, you can use the raise hand function. Additionally, if you have any technical issues, please reach out to the questions at Paleo Perks host. We have closed captions built into Zoom. You can use the closed caption button to show or to hide them. We're always looking for speakers for our seminar series, so feel free to nominate an outstanding early career researcher here, and that link will be shared in the chat shortly by the questions at Paleo Perks host. Additionally, we collect weekly feedback on demographic info. It's completely anonymous, optional, but it is encouraged. And you can also find that linked in the chat window soon. So a bit more about our speaker today. Jeet studied geological sciences, got a bachelor's degree at the Jadavpur University, and then went on to do a master's and a PhD at the Indian Institute of Technology, and also in geology. And Jeet is currently an assistant professor at the Department of Geology at the Jogmaya Devi College at the University of Calcutta. So with that, Jeet, I will hand over the presentation to you, and yeah, just feel free if you have any questions or any issues, just let one of us know.
Yeah, hello. Thanks a lot for giving such a nice introduction, and I will right now try to go ahead with sharing the screen and my slideshow then.
Yeah, you should be able to just kind of steal the screen share from me if you.
Yeah, I think yeah, I can do that. This is
Okay.
asking this will stop other screen sharing. Do you want to continue? Yes, I can continue like this.
Yep.
Okay. Yeah, I think right now it is visible. Yeah, my slide is visible, isn't it?
Yeah, we see your slide, but it's the not the presenter view. We see like all of your slide.
Yeah,
Yeah, now
yeah.
it's
Right now it is in presentation mode. Yeah. Yeah.
perfect.
Sorry for the trouble.
All
Okay.
good.
Right now I will slowly, yeah, start. Okay. So thank you, PaleoWorks, for providing me this platform to talk about, yeah, to start and talk about the research which I have done. So I will be talking about the reconstruction of monsoon-induced oceanographic conditions in the Eastern Arabian Sea since Marine Isotope Stage 3. It is precisely late Marine Isotope Stage 3 from last 40,000 years. Uh, so it will be insights from foraminifera and pteropods. And I also want to introduce myself that I am Dr. Jeet Majumder, as the host already introduced me. And before going into the data and the interpretation and the stories which I interpreted from the patterns, I will be talking about a bit about the introduction. So the work which I'll be presenting here, it was a part of my PhD work at IIT Kharagpur, Indian Institute of Technology, Kharagpur. So to introduce, I will be at first talking about the Indian monsoon system. You are mostly aware about what is this. This basically seasonal changes in wind direction. And because of the seasonal changes in wind direction, there are important patterns, like in case of especially Arabian Sea. For example, when there is the summer monsoon, the wind strength is very high. And in that case, there you can see that, as you can see in the chlorophyll A map to the right hand side, during the summer, there is rigorous, strong upwelling induced productivity happening in the Western Arabian Sea. It is also strong upwelling. At the same time, it is also spatially large. Whereas in the eastern part of the Arabian Sea, the upwelling strength is moderately strong and sometimes weak also, and the extent of upwelling is limited to a quite narrow zone compared to the western part of the Arabian Sea. And in case of the winter monsoon, what happens that the winds are not strong enough to generate the upwelling along the coastal regions, but the vertical mixing of the water occurs, and because of this, there is a limited amount of productivity happening. So, to understand the different oceanographic changes which happened since the main isotope stage 3, I selected an core which was collected during Sagar Kanya cruise expedition from NCPOR in India in 2011. And the core was collected from a water depth of 182 meter, and the total length of the core was 4.92 meter. So the core is located at the outer continental shelf to slope part of Eastern Arabian Sea here. And here I have shown how in different seasons the primary productivity that changes. And you can see that the core site is influenced by the primary productivity during this summer, but in the other seasons, the productivity is compared to the summer, the productivity is quite insignificant. It is only limited to the very narrow part of the coastal region, and that is mostly due to the coastal influx induced productivity. So, and here I have also shown a more detailed oceanographic setting of the study area. And here, what I have shown here, that you can see, yeah, just a minute. You can see that the core site is shown here. And as there is high primary productivity happening in the surface ocean, so because of the consumption of the organic matter, there is also generation of an oxygen minimum zone, and it starts from 150 meter of water depth to about 1,200 meter water depth. And to show the nature of oxygen concentration at the sediment water interface, I have shown here oxygen concentration map at the bottom water environment. So here you can see that the bottom water environment along the outer continental shelf of India, it is actually being touched by the oxygen minimum zone water. So that is why very low concentration of oxygen is here. So it should be reflected in the microfaunal assemblages, and that I will be looking and sharing with you. So after retrieving the core and general sediment processing was done following some standard protocols, and then the chronology was established based on 15 AMS states, and faunal assemblage studies were done, followed by stable isotope analysis of the microfossils, then scanning electron microscopy, and also EDX was also done. So I found the sediments quite rich in terms of different kinds of microfaunus, like starting from benthic foraminifera to planktic foraminifera, and also pteropods. And I also found micro in bivalves and also heteropods. But due to time constraints and other reasons during my PhD, because of the time was limited also, and so I was unable to provide an additional focus on heteropods. Maybe in future I will do, but I focused on these three major groups. So at first, I will be talking about the planktic foraminiferal assemblages, and they are linked to the monsoon-induced surface productivity in the studied region. So after looking at the uh, microfossil planktic foraminiferal assemblages, I found this species the most abundant planktic foraminifera species, which I have shown here by using box and whisker plot. And here you can see that the top three dominating species are, uh, first of all, Globigenoides ruber is there, followed by G. glutinata and G. bouloides. And after that, there is the Trilobatus genus. That group is dominant, and after that the dominating species are like G. menardi, Indutatory, Puleniatina obliquulaculata, and others are there. So I have shown the most dominant species here by using the ACM image plate. So based on the assemblages, I tried to plot a stack, make a stack plot, but individual species abundance can be confusing sometime because they will be dependent on various factors individually. So I have I have combined some of the species for productivity to indicate, for productivity, to understand productivity, I have overlapped the G. boulardis abundance and G. glutinata abundance, because they both provide information about the productivity or eutrophication in some cases. So in Arabian Sea, G. boulardis is an well-established proxy to understand the productivity caused by, induced by monsoonal winds, and G. glutinata is also to some extent known to be linked to the productivity. However, it is also known to be an opportunistic productivity indicator. So here you can see that in LGM, most of the planktic foraminifera group, they are showing a similar kind of, oceanographic story. For example, G. boulardis and G. glutinata, they are showing a decreasing trend from the beginning of the LGM to the middle part of the LGM. There is a decrease, suggesting a decrease in productivity, monsoon-induced productivity. And during this time, you can see that there is an increase in the oligotrophic planktic foraminifera group. So the oligotrophic planktic foraminifera group, it includes the most dominant planktic foraminifera G. ruber and the Trilobatus genus also. So they are actually increasing, showing finally high values at the middle part of the LGM. And afterwards, I'm sorry, and during this time, when the upwelling is supposed to be very weak, in that time the thermocline indicators species like Puleniatina obliquulaculata, that is also showing a very less abundance, suggesting deeper thermocline. And then the significant another significant trend is seen during the early part of the Holocene, when the productivity indicators are increasing, whereas the oligotrophic plankton foraminifera are decreasing, and the thermocline indicator, it suggests that there is a shoaling of the thermocline, and which is followed by a decline suggesting deeper thermocline in the middle to late part of the Holocene. And during that time, there is a slight increase in the oligotrophic plankton foraminifera group. And during that time, the upwelling indicator, that G. boulardis, is drastically decreased. But an interesting trend is shown by G. glutinata, possibly as the most favorable condition for G. boulardis actually decreased. So G. glutinata actually flourished by finding that opportunity. So as I have already told you that G. boulardis is one of the, indicator of monsoon-induced upwelling and productivity in the Arabian Sea. It is well known, and it is one of the major proxy to understand paleo productivity and paleo upwelling. So, whatever was happening in the eastern Arabian Sea, starting from the northern to southernmost sector, I have compared my data from some nearby sites. As you can see, this is my study site, and I have compared my data, G. boulardis data, with a nearby site and also a site from the northernmost Arabian Sea and southernmost Eastern Arabian Sea. So here is the stack plot showing the G. boulardis abundance in different sites, starting from northern to southernmost Eastern Arabian Sea. And here you can see that in the LGM, the productivity, the lowering of the upwelling induced productivity was not similar in every part of the Eastern Arabian Sea. It is known that in the Western Arabian Sea during the LGM, the productivity, the upwelling was distinctly decreased during the LGM in the Western Arabian Sea. But in case of Eastern Arabian Sea, you can see that in the southernmost sector, initially the productivity was much high, then it decreased. However, in the at my site, the productivity was not that much high, but it still decreased. And in the northernmost sector, the productivity was distinctly low throughout the LGM. And afterwards, all of them are showing more or less similar values, like during the early Holocene part. In most of the early Holocene, they are showing higher values, suggesting a higher intensity of monsoon-induced upwelling and productivity in along the Eastern Arabian Sea. So as we are starting our journey from the water column, what is happening at the water column? So there is another important group of microfauna which are relatively less studied in world ocean, that is pteropod. So I will be mostly talking about the pteropod state of preservation and their shell size in the Eastern Arabian Sea at my site specifically. So pteropods are basically, they are pelagic microgastropods, and they are also called sea butterflies. Like they are having two flap-like appendages, and they are not very active swimmers. They can migrate vertically. A lateral migration is very insignificant, and the present day surface distribution study of pteropods were carried out by Singh et al. 2005, and they showed that there is very high abundance of pteropod in the shelf to slope sediment of the Eastern Arabian Sea. So this uh, this actually provided me an opportunity to look into the pteropod assemblages uh, in the past, geologic record. So based on that, I analyzed the sediment and found various pteropod species, and were also preserved nicely. And here I have shown some of the most abundant pteropod species found in the sediment of SK291GC17, studied 4. And here I have shown box and whisker plots showing their abundance during the study time slice. Here, this is an enlarged form. And from the graph, on the left hand, you can see that the most dominant pteropod species is Heliconodis inflatus, followed by Limacina trochiformis, then Limacina bullimoides, then the genus Cresseis is there, then Gleba cordata, and there are other minor pteropod species. Now, I have plotted the relative abundance of the major, most abundant pteropod species here, and you can see that the lowermost one, the relative abundance of Heliconodis inflatus, H. inflatus, that is showing quite a different kind of trend with respect to the above four species or group. So there is something interesting to get from this species. I will go there slowly. And one thing, I also combined all the pteropod species. I subgrouped them by combining based on their depth habitat. Like the epipelagic pteropods, they are thriving in the uppermost part of the water column, and the mesopelagic pteropod, on the other hand, they are thriving also at the deeper part, because they can migrate vertically at day and night in search of food maybe, and there are some other factors which are not that much known, but the grouping is based on some already studied informations, like their depth habitat are known, uh, the depth habitat of this species. So the interesting thing is that though the depth of my study site, that is about only 182 meter, uh, but the mesopelagic pteropod, who are supposed to vertically migrate, like more than, they can also migrate up to, more than 200 meter at water depth in some cases, but they are thriving more in the shallow sea compared to the epipelagic pteropods who are supposed to thrive in shallower water. So there must be other reasons other than bathymetry, which are driving their changes in abundances. So this is just a biplot to show that Heliconotis inflatus is quite different with respect to the other abundant pteropod species, whereas Limacina bullimoides, Brachypyrmis, and Trichices genus Cresseis are quite similar in terms of their response to the oceanographic changes. So, how the pteropods are important and what is the reason? The main reason is the nature of their shell. Their shell is made of aragonite, and because of the metastable nature of the shell, they are very much sensitive to the change in environment. Like if there is even a slight acidification of the ocean water, then the quality of the shell changes drastically. For example, this is a live shell of a pteropod species, Limacina helicana. And before any environmental stress, it was smooth. But when there is dissolution due to some environmental stress, like corrosive ambient water, ocean acidification, this kind of thing, so the shell becomes progressively more opaque, white, and the surface features are more uh, more abraded, and we can also find some weak spots, breakage, dissolution features on the shell surface. So based on these rationales, there are some methods to understand, to trace the effect of dissolution on the pteropod shell. So there was a scale developed by Gerhard et al. 2000, the Limacina Dissolution Index, and it can help us to evaluate the extent of dissolution on the pteropod. So LDX is a scale based on qualitative analysis of the surface of Heliconotis inflatus. And why Heliconotis inflatus? It is most abundant, first thing. And secondly, Heliconotis inflatus is one of the most delicate pteropod species. So it is a very good proxy to understand a very small change in the ambient water. So in case of LDX, a scale of 0 to 5 is applied based on the transparency and preservation state of the shell. Like for LDX 0, the LDX 0, the shell is transparent and there is no dissolution feature on the surface. But in case of LDX value 5, the shell is actually opaque white and the surface of the shell is extremely perforated, and there are numerous dissolution marks on it. And in my study site, I only found preliminary stages of dissolution in H. inflatus, starting from LGM to recent, and because of the preliminary stage of dissolution, the LDX value actually varied from 0 to 2 mostly. So I also looked at the shells under the stereosome microscope, like the optically, when the shell is transparent, I checked the similar kind of transparent shells under the using the ACM, and found that yeah, the shells are showing smooth surfaces. When under optical microscope it is transparent. So yeah, I also measured the average shell size of H. inflatus, because to correlate with whether in different oceanographic condition the shell size is increasing or decreasing. So here I found very interesting trends, like when the Heliconoidis inflatus abundance is very less, the shell size is also less. And when the abundance actually increased, the shell size increased. So there is a chance that when the Heliconoidis inflatus, it is thriving more because of more productivity, and it is thriving less. In case of less productivity, the shell size is also less. And when the shell size is actually larger, it is basically getting more food, possibly. But there are very less number of studies actually to support this hypothesis. But mostly it was the reason for which the shell size increased. And I also tried to see whether the dissolution had any effect on the shell size. So when I plotted, the LDX values are plotted here, and you can see during most part of the studied interval, the LDX values are not much high, only except the late Holocene part. And here I have also plotted the ratio of opaque H inflatus. What I actually did, the fraction of sediment which I studied for H. inflatus abundance, I also counted the opaque shells in that entire assemblage. So to get an overall understanding, like whether the whole population is getting affected due to dissolution or not. So basically, I was trying to work on an additional kind of proxy to understand the dissolution. So both of the proxies, whether it is ratio of opaque shells or LDX value, they are suggesting higher dissolution during the late Holocene. And what I found that it might be because of the influence of the oxygen minimum zone due to the sea level rise. What is happening here, as my study site is only about 182-meter water depth, at 182-meter water depth. So basically, before the rapid rise of sea level during the early Holocene, the study site was supposedly below the upper horizon of the oxygen minimum zone. So it was not getting affected by the OMZ water. But as the sea level was rising, the oxygen minimum zone, it actually touched the study site. And after the death of the pteropods, the dead shells were actually subjected to corrosion. That is getting reflected by the LDX and ratio of opaque H inflatus values. So, one thing I just wanted to show you, that the shell size in H. inflatus and the relative abundance of the species are showing very good positive correlation, suggesting that when a favorable condition is actually present for its increase in abundance, it is also allowing the shell size also to increase. And I have just included a recent study to show the significance of the importance of LDX compared to other methods. Like Quester et al. They have shown that ACM is ideal for very precise dissolution features and to detect the onset of dissolution. However, LDX, on the other hand, is a fast and cost-effective metric, and it is also strongly correlated with ACM related methods, regardless of the oceanographic conditions. So I already talked about the processes which affected the microfauna in the upper part of the water column. So whatever was happening in the upper part of the water column, definitely it also affected the bottom part, the benthic environment, because the water depth is very less at this time, only 182 meters. So I'll be looking at the assemblage of benthic foraminifera and showing you how I traced the possible signatures of coastal hypoxic events in the Eastern Arabian Sea. So at first, I want to talk a bit about the TROX model. TROX model was actually coined by Joyson et al. 1995, and it is basically a model to show that a benthic foraminiferal microhabitat is dependent on the uh, availability of food at the surface of the ocean, the food flux. So it will basically control whether the microhabitat will be oxygen controlled or food controlled, and depending on that, there will be an increase in the infaunal elongated kind of benthic foraminifera. On the other hand, if it becomes a food controlled oligotrophic condition, then we can find more oxic benthic foraminifera, which are mostly epibenthic kind. So I subgrouped all the species of benthic foraminifera in oxic and suboxic to dysoxic group. So here a very interesting trend is seen, like during the MIS3, you can see there is immensely lower abundance of oxic benthic foraminifera, and at the same time there is very high abundance of dysoxic to suboxic benthic foraminifera in that time, and the diversity also was very low because of the low oxygenated condition possibly. So I compared it with the data from the upper water part of the water column, and here I have compared with the G. Bollardis data from the same core, and you can see the upwelling induced or the monsoon induced productivity was very high during the MIS3 in the Eastern Arabian Sea at my site precisely, and possibly this eutrophication of the surface water, I mean more eutrophication or eutrophic condition in the surface water, we might have driven the hypoxic condition at the benthic environment. So I also tried to see the geochemical changes in the sediment, and from the same core, one of my senior actually did this thing, and here based on different chemical parameters, I saw that the siliciclastic sediment content is more during the MIS3, suggesting a possible influx of more siliciclastic material from the uh, hinterland, and the chemical indicators, they are also indicating that the source rock weathering was much higher during the MIS3. Iron content is also high, and possible anoxic condition is present. So I looked at the ACM just of like some foraminifera. It was containing, the specimens were containing sediment infilling inside the shell, and I looked at many specimens from the MIS3 section, and I found that there is a, signature of iron and sulfur in the sediment infill here, like the spectrum 2 is showing. And when I looked, when I took a closer look, and I found that there is the presence of rhomboidal pyrite aggregates, and also there is presence of euhedral pyrite crystal. So there is a signature of pyritation in the study area. So basically, what happened in the Eastern Arabian Sea between this time? So what happened? Possibly high productivity and increased continental influx due to the intensified ISM actually caused us under relatively lower sea level compared to present, and also the Holocene, the seasonal eutrophication actually occurred. And parallelly, what happened? due to the shallow sea level, um, what happened that there was uh, possibly, as the sea level was lower, the coastline was actually relatively closer to the study site, and it maybe allowed the increased erosion and influx of iron-rich sediment to the study area from the uh, hinterland, which is known to contain iron-rich sediment and rocks. So, because of both of the reasons parallelly, it actually allowed the increase in disoxic to suboxic benthic foraminifera and also allowed the formation of pyrite. So there are many things to look at and also talk about in conclusion, and also talk about what are the future prospects. But a few points only I will only raise here. Like in the Eastern Arabian Sea, the monsoonal wind has influenced the assemblage of different microfaunal assemblage since the MIS3, and the low sea level, increased continental influx, and high productivity are some of the factors driving the hypoxic condition and also oxic condition in the shallow waters. And if the water is aragonite saturated, then productivity it may become one of the major factor behind the higher abundance of and the larger shell size of some pteropod like H. inflatus. So I want to thank Paleoparks committee for providing me this opportunity to talk, and I want to thank many people which contributed and helped me to generate the data and work. Thank you.
Great. Thank you so much, Jeet. That was a very interesting talk. If it's all right with you, we
Uh,
can kind of roll right into the question and answer session. We already had a
uh,
couple questions submitted.
so should I stop the sharing right now? I can.
Actually, if you want to just leave the screen up in case some of the questions,
Yeah, I
maybe.
can't see anything right now. So I will
Uh,
stop sharing. I will stop it.
okay, yeah. Um, so sounds good. So we already have a couple questions that have been submitted. Just a reminder to anyone in the audience, if you have questions, you can submit those via the chat to the questions at PaleoPerks host. But I can share the first question here that was submitted. And this question reads, what do you think could be a reason for the positive correlation between abundance and shell size? Do you have any ideas or hypotheses on that?
Yeah, I have one hypothesis that if like the availability of food is much more. The thing is, okay, I will start from a bit from the basics. Like in case of pteropods, their abundance are mostly known to get affected by the saturation of aragonite in the ocean water. So suppose the ocean water is already enough aragonite saturated. So now there will come additional factor which will be influencing their abundance as well as the shell size. It should. So in the Eastern Arabian Sea and in every other part of the ocean basins also, world ocean, like when we are dealing with shallow sea, so there the aragonite water is already aragonite saturated, mostly, most of the time. So productivity, as we know, the productivity can influence the shell size or the test size of like even foraminifera, even other organisms, microorganisms. So there is a chance that the shell size of pteropod is also getting influenced because of the availability of uh, food in the upper part of the water column. That is a possibility. What I have.
Okay, that makes sense. Great, thank you for that response. We have another question, which I will share in the chat. Okay. This is maybe a slightly longer one. During the late Holocene, the G. boloides and G. glutinata show a reverse trend. However, their trend is the same during the LGM. What could be the possible reason for it? what about the seasonal control for G. boloides and G. glutinata and how they behave seasonally in the modern environment in the Arabian Sea?
Yeah, that is a very long question. The thing is, the problem mainly arises in the Eastern Arabian Sea. That the main reason is because of uh, the extent of the upwelling zone in the Eastern Arabian Sea. Like when the upwelling zone is very, I mean, literally very vast, it becomes easier to be tracked by the microfaunal assemblage. I mean, as a proxy. But in case of Eastern Arabian Sea, the spatial movement of the upwelling zone can also influence the uh, plankton foraminifera. For example, G. boloides is known to proliferate in the core part of the upwelling zone more, whereas the G. glutinata, it is in many parts of the world ocean, it is known that it can thrive more in the periphery of the upwelling zone. So I think that in the before the late Holocene, I mean during the LGM, I mean before the late Holocene, uh, the upwelling zone was actually residing more over the studied site. But when the sea level actually was rising, the upwelling zone actually shifted away from the studied site. That is my site. Actually, it shifted away and moved towards the coastline, possibly. So not only the weakening of the upwelling influenced the microfaunal assemblage, but also uh, the shifting of the upwelling zone. It can be another reason which influenced the abundance. It can be like a similar study I saw in case of the northwestern Africa, where the shifting of the uh, upwelling zone actually influenced the assemblage quite a lot. So that can be a reason. And the thing is, the question is quite long. I don't know whether I will be able to answer every point, but I think I will try. So seasonal control, I am not sure about because in case of Western Arabian Sea, there were some studies, and what I have seen that G. boloides it reacts first. I mean, it comes first when the upwelling actually initiates. The productivity actually rises, and the G. boloides actually it is the first to proliferate, and other species actually come a little bit late after that, mostly. So in case of late Holocene, possibly because of the sea level rise, shifting of the upwelling zone, and also the weakening of the upwelling event, actually G. glutinata found it more favorable, and it actually took the opportunity compared to G. boloides. Possible.
Great. Thank you so much. I think you did a really good job of answering the multi-part question. So thank you for that very thorough answer.
Yeah, thank you.
We have a couple questions left. So just a reminder to anyone in the audience, if you have any pressing questions, please try to get those into us. Otherwise, we'll wrap this up after the last question. The next question reads, does pteropod shell dissolution have greater ecological impacts due to food web disruption or ocean chemistry fluxes, as far as you know, or as far as you hypothesize?
Does pteropod shell dissolution have greater ecological impacts due to food web disruption or ocean chemistry process? I am facing a little bit difficulty to track the question, what it is, what it means. Like, can it be more clarified, the question actually?
So I think this was getting at, does as the shells kind of dissolve, does that either the weakening of the shells and therefore the
Okay,
weakening of the organism, does that impact
okay,
maybe food
yeah,
web dynamics?
yeah, the ecological or food web, yeah, the impact is there because pteropod, first of all, as a food source for the marine organisms, it is one of the major food source in the ocean water column, one of the major food sources. And secondly, regarding the chemistry flux, like uh, because uh, it is a contributor to the carbonate flux. So when there is excessive resolution of the pteropods, so the carbon flux is also reduced, and it is basically disrupting the carbon cycle. So excessive resolution because of anthropogenic activities like increasing CO2 and these kind of things, ocean acidification can impact a lot.
Okay, I think that makes sense. I think that kind of gets at the what the question was going after. So thank you
Yeah,
for that.
possibly.
Uh, Great. Then we have one last question that has been submitted to us, and then we can wrap up. Uh, and maybe there's a quick answer to this. Maybe there's more. Maybe you can elaborate more. I don't know. But it asks, is there a greater environmental reason that diversity was so low during the MIS3?
Yeah, there can be another reason, but I'm not sure whether that can be a, I mean, major reason. Like in the shallow, uh, I mean, shelf area of the Arabian Sea, Eastern Arabian Sea, there were some reported events of methane degassing, methane seepage. So when there is methane seepage happening at the benthic environment, there is a chance that the disoxic to suboxic benthic foraminifera will thrive more in that kind of environment. But to track that, I think more multi-directional studies should be done in this code to conclude anything.
Great. Thank you so much.
Yeah, thank you.
So with that, I think we can wrap up our question and answer session. I will just share my screen quickly for a couple last announcements, but I just want to say, there we go. Jeet, thank you so much again for a great talk.
Yeah,
Um,
well,
yeah, it was a lot of fun, and thanks for responding to the questions. So just a reminder to the audience members, we ask you to please fill out the weekly feedback form, which will be linked again in the chat. And just a reminder that next week on September 16th, we have another seminar also at UTC 1500, which is going to cover ice cores and paleoclimate by Peter Neff at the University of Minnesota in the United States. So we hope to see you then. And with that, for anyone who wants to stick around and maybe ask a couple more informal questions, we can have a tea time after this. And if not, we'll see you next week. So for those who don't really know how tea time works, we normally have a 2-minute break. So you can get up, grab a drink of water, and then we'll reconvene here in 2 minutes and we'll kind of just see who wants to stick around and see how things go. So anyways, thank you again, Jeet. And
yeah.
to the people in the audience, thank you for coming, and we hope to see you soon.